Okay, hello, good evening. Hope everyone's doing well. Mike, okay. Got Mike. Um, okay, we're in week 14. Hello, baby doll. Hope you're doing well. Nice to see you here as always. See Damien in there as well. So, hello, hope you're all doing well. Um, okay, so I know you just got through with it's the grind that is programming classes as you get more advanced, is that you always have you just put something away and now there's something new. So um, tonight we start our last sort of sprint toward the fourth individual project uh, that's due at the end of the 16th week. During the week of finals, we do one more lab for something that I want to expose you to, but you will have already done the last project. Okay. Week 14. So these next 3 weeks are all oriented toward giving you what you need to solve the fourth individual project. I'm actually going to look at that first. Let me open it up, make sure that you are looking at what okay, so you can see. Okay, so the fourth individual project, it's going to feel very similar to the project that you just finished. We're going to have a file of commands. We're going to read in the commands. We're going to use the commands to figure out functions to call, and then we're going to have an output that we're trying to produce that matches the expected output. So if you go look at individual project for repository, it looks very much the same because it's the same setup. So hopefully that comes as a relief to you that the setup is the same. So you're going to be getting a file, you're going to be cycling through the file, you're going to be picking off commands and then applying those commands to a data structure. One thing that should please everybody is that there are way fewer commands to deal with on our new data structure. So that's the whole list of required inputs that your program has to handle because while our structure, good evening, little peeper, hope you're doing well. So you'll see here when you start looking around at the fourth individual project, the setup is the same, except for we're using a different data structure. And the data structure has fewer commands that it supports, but coding it is more complicated. So the next 2 weeks we're going to code most of the data structure as part of our lab work. So just a heads up about that. You'll notice when you go to look at the files for individual project for same kind of deal. Required operations, required outputs, same deal that you just experienced in project 3, but with a new data structure. Okay, so that's that stuff. Week 14. Okay, so we're doing a new data structure this week, and it's called a binary search tree. So I'm actually going to switch just right off the bat. I'm going to switch and draw pictures. Apologies that I'm never going to be good at this, but I just want to show you how heavily I lean on the picture drawing and hopefully encourage you to try it for yourself. I noticed in chat in Piazza that a handful of people did mention drawing the pictures, so it's something that you have to practice, actually drawing the picture, but it's so helpful to find bugs in your code if you can just learn to draw pictures. Okay, so our new data structure is called a binary search tree. I'm leaving some space here. Oh, that's good, Damien. So you figured out how to, you've been working on your picture drawing skills. If you go into any professional programming shop, by the way, they're going to have whiteboards because people draw pictures of stuff. And it's very helpful in a language like C++ when you have pointers all over the place to try to identify what pointers matter at any given moment in time and possibly where your code is broken. So we are adding binary search tree. new data structure. So the data structures we've dealt with so far, the doubly linked list, singly linked list, vectors. That's the main ones that we've dealt with. We've talked about array a little bit, although I haven't required that you use them anywhere. So these are all the collections that we've dealt with in this class in some form or another. At the end of the semester, by the way, we're going to do a hash table. So you'll also get exposed to how hash tables work, at least very basic ones. So one thing to understand about all these data structures is why do we have different data structures? And the reason is because what we're often doing in programming is we're taking some data from somewhere in the world, from users on the internet, from a file that has information in it, from a database. We take information from some source and we model it in the computer. So we take it and we turn it into variables. And sometimes we package those variables up either into a struct or a class. And then usually, once we model the data in the computer, then we need to put it somewhere where it can be easily accessed and manipulated later. And that's what these data structures are about. We get some data, we load it into a model, and then we take the model and we store it in some data structure. This is part of sort of building up your experiences in computer science, is to understand what kinds of data structures are out there. And then over time you begin to understand when one data structure might be better for a situation than another data structure would be. So I know that you kind of get lost in the code because it's so complicated. But I thought I'd stop here for just a few minutes and talk a little bit about the differences and then the strengths and weaknesses of these various data structures. So arrays are the most fundamental data structure in many languages. So their strength is that they are very fast. They allow you to do random access of data with an index. So you have the power of using an index to target specific pieces of data inside of the structure. That's their main advantage. The main disadvantage of an array is that it is statically sized. Once you've sized an array, you can't make it be bigger and you can't make it be smaller. So arrays are really good when you have a fixed amount of information and you know exactly what that fixed amount of information is. So vectors are very much like arrays. The difference is that they give you the ability to grow and shrink. They actually don't perform very well. They're not the most efficient use of the computer's processor or memory because every time they have to grow, they actually have to do a whole bunch of allocating memory and copying data. They actually make a whole new bigger vector and then copy the data from an old vector into a new vector is how they do it. So vectors are very similar to arrays, but a lot of programmers love them because they're so flexible, because they will grow as your data grows and they will shrink as you remove data. So they are a powerful data structure, but really they're just sort of a different take on the array. All right, so then we get to the linked lists. So we've done a singly linked list and a doubly linked list. The advantage of the linked list is that they perform a lot better than vectors do for growing and shrinking. So a vector to grow actually has to create a whole nother larger vector and then copy stuff from an old vector into a new vector and then eliminate the old vector. Whereas a singly linked list, you literally just create a single new node to hold the single new piece of data and then you link it in. Same for doubly linked list. So singly linked list and doubly linked list are very, very good for handling unknown amounts of data coming in. Because you get new data, you make a node, you attach it to the list. One thing that you know that they're not very good at, because now you've written code for them, linked lists are not very good at accessing information in the middle. So unlike arrays and vectors that allow random access using indices, there's no concept of random access for a linked list. You have to start at one end of the linked list and iterate over it until you find what you're looking for. That was like our get function on the doubly linked list. So these are not good data structures, linked lists, for situations where you frequently have to randomly access data. So they just give you an option for a different situation. One thing that they are good at is working at the ends. So if you are only like front or back, then doubly linked lists perform quite well. But when you have to go off into the middle, linked lists don't perform as well. And you've seen the code, how complicated it can be to try to keep the data inside of a linked list in order in some fashion. So they're not very good at that either, at keeping things in some specific order. So they're good for dynamically growing and shrinking. They perform well at that. They're not so good at ordering themselves, and they're not so good at finding random items in the middle of the list. Okay, so that's those two. So we're adding binary search tree. So this one's the first data structure that we have that is sorted by design. So binary search trees, there is no concept of a binary search tree being unsorted. That we call it a binary search tree, the search part tells us that they are always sorted. It's impossible to have a binary search tree where the data is not sorted. So that's immediately an advantage over these other data structures we've seen, because none of these by default orders itself. But a binary search tree, every time you add information, it is added to the data structure in a location that it is always sorted. So they are always sorted, which is a good thing. They're dynamic. So they're based on nodes, like linked lists are, which means that they are very good at taking in new data, an unknown amount of data over time. They're very good at that because you get new data, you make a node, and you put it into the tree in the place where all the data remains sorted. So that's quite nice about the binary search tree. What else do we know about them? Something that you're not going to like about them. They rely very heavy on recursive algorithms. So one of the reasons why we did the warm-up lab with recursion is because we're about to start writing binary search tree algorithms, which are all recursive. And there are other ways to do it, but by far the easiest way to code a binary search tree is with recursive algorithms. Good evening, Shugam. So anyway, heads up about that. You're not going to like it at first, but it's super powerful, and the functions become very small because they're recursive, but they are more difficult to reason about. Okay, so the binary search tree, what's good about it? It keeps the data sorted always. It's dynamic like linked lists, so it can take in a lot of data over time, and you never have to worry about how much data it's taking in. The algorithms are recursive, which means that for programming's sake, that makes it slightly more complicated. Let's see. They don't have the concept of random access like an array. So to find data in a search tree, you have to iterate them like you would a linked list, but you'll see when I start drawing pictures that finding the data in a binary search tree is much faster potentially by half as much as a doubly linked list is. So they don't have random access, but because they are sorted and the way that we structure them, the they make accesses faster than they might be otherwise. So no random access, but relatively high-speed access, even though the tree does have to be iterated. Okay, that's the main points about a binary search tree. They're always sorted. That's what makes them a binary search tree. They're dynamic. They use recursive algorithms. They don't support random access. Deleting data from a binary search tree is a difficult algorithm. We'll do that one together. Much more difficult than linked lists. Technically, you can't even erase something from an array. A vector you can. So the recursive algorithms and the fact that the deleting something from a binary search tree is harder things to just be aware of. We will get there and work through it together. Okay, so that's just a rundown of data structures. If you go start doing research on like geeksforgeeks.com, you'll find that there are lots and lots and lots of data structures. So after this class, if you were to continue your studies, the next step would be to implement and explore algorithms for more even advanced data structures. There are fancier versions of trees that we use for building database products on top of, for example. There's a data structure called a graph that we use for routing, we'd say, so routing traffic over the internet. So anyway, there's more data structures is the point. This is just a taste of the most basic ones. But now we're at the sort of high point of your college career, which is the binary search tree, and that's the biggie for us. Okay, so what do they look like? So they're built on nodes. So I'll call that a binary search tree node. Looks very similar to what you're accustomed to. It's basically a container for data, and it has two links. But the links conceptually are different. The links are more like building a family tree. So we're going to call the links in our code the left one and the right one. So those are both pointers to other nodes. But conceptually they point down so that we can use them to construct something that looks like a family tree. So that's what a node looks like. The tree itself looks like this. It's a single pointer to what we call the root of the tree. So the root of the tree will be a node, and I'll draw you a bigger one. So binary search tree nodes have a field for the data, and then they have pointers to a node going down to the left and a node going down to the right. We might end up calling these children of the node. So they have a left child and a right child, and then the tree structure itself just keeps track of a single node, which it calls the root of the tree. So I'm going to draw a bigger one here with stuff in it. Okay, so here's a tree that has some stuff in it. Just as an example. So here's what trees can end up looking like. Is a bunch of nodes chained together in a family tree. Here's the root node, and then you have the root node's left child, right child, the left child's left child, the left child's right child, the right child's left child, and the right child's right child. And then we have these nodes who have no children, which we don't need this really in our code, but you'll sometimes see people call these leaf nodes. So you're on the branch and then you hit a leaf because that's the end of the branch. But any node that has at least one child is not a leaf. So anyway, this is what they look like if you were to draw a picture of them, a binary search tree. So you can see how we structure it with the left and right. So notice here there's no right child off this one, no left child off this one. So here's a leaf, leaf, leaf. That's what a binary search tree can end up looking like. So now let's build one just by drawing a picture so that you can understand how we sort them. Okay, so if we have a tree to start, the root pointer is going to be pointing at null. There's no node there. And the only way to get data into a binary search tree is with one insert function. So we're not going to have push front, we're not going to have push back. There's no concept of front or back. The only way to get data into a tree is to insert it. And the reason for that is because the data always remains sorted. So here's how that works. The first thing to be inserted in a tree, I'm just going to insert 50. When the root is null, then the first insert becomes the root node. So we'd end up with a node containing 50. Which is the root of the tree and also a leaf because it doesn't yet have any children. So the first insert on every binary search tree ends up at the root, no matter what. So now let's insert some other stuff. So let's insert 25. So the way that we're going to design these algorithms, whenever we insert data on a tree, we go left every time we have data that's less than the node that we're on. So to insert a 25 in this binary search tree, we start at the root. If there's something at the root, then we have to decide if we go left or right. So since this is 25, we're going to go left. There's a space there, so we can attach the 25 right there. So the root remains the same. The newly inserted data now becomes a leaf, no children. The root's no longer a leaf because it has a child now. So it's going to look funny in a second, but it's like magic once you learn how to code it. So if I were to insert 75, then if we were to start at the root, which is where you always start with a tree, we have to decide based on what we want to insert if we go left or right. Less is left, more is right, so this is more. So, and then we have a space, so we put the 75 in there. So let's try something easy and then something hard. So let's insert 20. So to insert 20, we start at root, we're less than that. And then we get to a node that's not a space, so we have to do the comparison again. So lesser or greater, where we are lesser with 20. So we go down again to the left, and there's a space, so we can put the 20 there. So now let's do insert 30. So we start at root. We're less than root. So we go to this next one, where we are greater than this one. So we go to the right, we find a space, we attach the 30 there. Now, this doesn't look... yeah, so Shugam asked, can I think of this as sort of like the root directory in a Unix file system? Sort of you can. I mean, this is sort of where everything begins. So in the sense that the root node is where the entire tree structure begins, yes, you certainly can. The difference is that in the Unix tree, you can have many children off every subdirectory, and in a binary search tree, you can only ever have at most 2 children off of any node. Okay, so now that we have the 30 in there, it may not look like this is sorted anymore. So, so we followed the rules. Okay, so Damien asked, what if you have the same number? So we are not going to insert duplicates. So that's a good question. What happens if we try to insert the same value twice? And for our application, for our binary search tree, we will refuse to insert duplicate data. That way we preserve the ordering that we want on our tree. So excellent question about duplicates. So we will not insert a 30 or any duplicate data. Okay, so how is this still in order? This is where getting a whole bunch of practice in recursive thinking can help you see this. But I'll just show you, I'll explain to you how I work this out. So we have this tree. I know it's sorted because I followed the rules, but how does that actually mean that it's sorted? So the way to think about, at least one way to think about how these work is that a binary search tree is actually many, many, many trees, potentially. There are as many trees as there are links. Because if you think about it, if I go left from 50 and I isolate this, that's kind of its own tree. And if I do that, do you see that this tree on its own is actually sorted left to right? So it can be very helpful for developing these algorithms to think of the tree as a series of a whole bunch of smaller trees that have been connected together. So if we were to count the number of trees that are here, we've got the big tree that starts here. We have this tree down the left of this tree. So left of 50 is a whole nother tree that's so this is a child tree of 50. This is a child tree of 50. And if you look at the data, everything in the child tree left of 50 is smaller than 50, which is the whole rule. And everything to the right of 50 has to be larger than 50. But if we keep going, if we go to the left of 25, that's another tree. And everything in that tree also has to be ordered. Left is smaller, right is bigger. Although here we get to a tree that has no children, so it's just a one node tree. Here's another one. So that's all the trees with nodes, but there's actually more trees because this is a tree, but it's empty yet. It doesn't yet have any residents in it. This is a tree that's empty. This is a tree that's empty. This one's empty. This one's empty. This one's empty. So if we were to deconstruct the big tree, we have all of these. We have one big tree and then two smaller children of the big one. That's 1, 2, 3. Here's a fourth tree, but it's empty. Fifth, sixth, seventh, 8th, 9th, 10th, 11th. If we were to deconstruct this down to every one of these smaller trees that's in here and all their subsets, sort of, we actually have 11 trees all hooked up together in various ways in this structure. So the reason I'm explaining it this way is because when we do an insert, assuming it's not a duplicate, what we're actually looking for, we want to descend through a series of trees until we find the empty tree where this one should be. That's our goal, is to start at the root and descend through the levels of trees until we get to an empty one where this one should be. So if we take a 90 and we start at the root, well, there's already something there. 90 is bigger than 50, so we go to the right into this tree. So now we're actually working in its whole own tree in there. And look at that, I could do that little, except for the shadow. Anyway, so now we're on this tree, trying to insert a 90 into this tree, which we know is a subset of this tree, but now we can just worry about this tree. And it's not empty, and we need an empty to put this in here. So it's not less than, so it's greater than, which brings us to this tree. And once we get to this tree, we find it's empty, which means that we can now connect a new tree and create a whole new sort of subsection of the larger tree. And then the rules still apply, right? So now we have these two empty trees below 90 that can take data. The 75 tree follows the rules. There's nothing to the left, but the thing to the right is larger. And then everything in that tree is larger than 50. And then down to the left, everything's smaller. If we take the subtree 25, everything to its left is smaller. Everything to its right is larger. There's a magic about that. So this one is in order, and the magic is that if you understand that working on a big tree is really deconstructing it to find the smaller tree that you want, then it can help write these algorithms. So binary search tree, it's a pretty neat thing. That sounded like Martha Stewart a little bit, if anyone knows that reference. Okay. Okay, so good question. So Little Peeper asks, how do we iterate this thing? You always have to start at root. So it's an excellent issue to bring up, Little Peeper. We always have to start at root. So there's no random access, and there's no concept of sort of keeping some marker down in the tree deeper somewhere that we can start at. You always have to come in at the root and then find your way to the data. But your question brings up one of the strengths about a binary search tree. If you notice, what's happening here is whenever I go to search for data, so let's say now I want to go find 90. I start at the root, but the moment that I have left the root to go in the correct direction, 90 is greater, so I'll go see if I can find it down this side. Potentially I have left behind at least half of the data. So one of the advantages of a binary search tree, and it's one of these twos are the reason why we call it a binary search tree, but really why we call it a binary search tree is because we have cut in half the amount of data we have to seek through to find things, because, or at least potentially half, because half of the data we just left behind the moment we went right. And every time we go left and right, we reduce the search space, we eliminate data we don't have to seek through anymore. So imagine if this were in a list, even if it were sorted, by the way. If this were in a linked list, and I wanted to find 90 in a linked list, I would start at the head, and then I would have to iterate 1, 2, 3, 4, 5 steps to get to that 90. So in a linked list, that's sort of a worst case scenario. A binary search tree, on the other hand, because of the way it's ordered, if I look for 90, well, the minute I go right, 3 steps went away. So there's 1 step, there's 2 steps to get to that same 90 in a binary search tree that took 5 steps in a linked list, even though it was sorted. So it's that binary search, which is cutting the amount of values you have to search through in half by 2, is one of the huge advantages of this structure. Pretty neat. Good question, too. Okay, so now let's go look at the code, and I'm probably going to have to flip back and forth just a little bit. Okay, so what can you see? You cannot see this depth. Okay, so I'm going to go in and grab some stuff out of this week's lab and then go into REPL it. So I'll step through there, so if you're doing a little bit of setup, you can do that while I'm talking this through. Lab 14. Okay, so we are starting to build a binary search tree with only the most basic functionality. So we're going to be able to insert. That's create, by the way, in CRUD. In CRUD terms, that's the C of CRUD. Inserting a node. The P is the R, the read. And then we will write an algorithm that deallocates all the memory associated with the nodes. And then you're going to see a funky thing here that I do with public and private functions. Okay, so that's the goal anyway, to begin implementing a binary search tree with the basic C part of CRUD, insert data, R part of CRUD, which is allow us to read the data back out, and then some memory management to free or delete the nodes we've allocated, and then finally I'll have to describe for you the setup, because we are using public and private functions. Supplemental videos as we've been doing since week 9, so same material and tons of spoilers, but I feel like I owe it to you to do something live and get your questions and your ideas. So, but those are there for your review, and you'll see that I've gone through the same material, probably in a slightly different way. Just because I would get bored if I don't change it up a little bit. Let me open, I'll come back to this. Let's see what else is going on this week. Some of you have already started working on this, so this is one of those just sort of brief internet search. The reason I'm asking about the principle of least privileges is because we are using private functions, and so I want you to have a sense of why and where that comes from. And then initialization lists, which I will incorporate into our code as well. And then the reminders. So lab as always, discussion as always. I know this is Thanksgiving week, at least for some of us. Well, not for me, it's just me and my wife. But for some of you, you may have things, work or other plans to do. Anyway, Butte College does Thanksgiving week school, so sorry about this. But hopefully you don't find them too much work. And then last project, sooner than later we'll start looking at that. That's it. Okay, let me go get some code. I'll open up this doc test so I can grab that. Yep, I'm going to need it. So let me start a replet and then move some code around. So setup is all I'm doing right now. So I saw, all right, I need doc test. I need bstree.hpp. So this is going to be a templated class. You have experience with templates. But it's already set up, so we just need to start coding the thing. bstree.hpp. bstree.hpp. And then I'll go grab the unit test code. Put that in main. Okay, so don't really need that for now. So the binary search tree, let's, you know what, I should put the code for it. Did I just put the binary search tree code in here? No. I just forgot to copy it for whatever reason. I hope I didn't overwrite something. Did you do something dumb? No. Okay. So we'll first look at the code, just make sure we understand basically what the code's doing. I guess I better leave my document camera. So it's templated. So the contents of the nodes will be T, whatever that is. Waiting for a constructor, waiting for a destructor, get size. You've seen these things before. Clear is different for a binary search tree because the process for clearing a tree is recursive. So we're not going to use loops, we're going to use recursive algorithms, which means functions that call themselves. Insert. So Damien asked, I think it was Damien, right? About the duplicate. Yeah. So the reason why insert returns a bool is because we're going to return false on duplicates. So we won't allow duplicates. We'll insert, we'll return true if it's a unique piece of data, but if we run into a duplicate, we're going to return false and not do an insert. And then we're going to do just a crude printing so we can see what's inside the tree. And if we look at the private section, this one's going to be a little bit scarier than normal. Well, the node part isn't too bad. So the data that goes in a node is the templated type. We don't know what it is. It'll be whatever it is. The 2 pointers, left child down to the left, right child down to the right. And then the constructor, let me unravel this a little bit so you can see the parts, what they look like. So what I'm using for the constructor here is called an initialization list. Somebody already went into the Piazza for this week and answered this question. This is called an initialization list. You need it when you do inheritance in C++, which I'll try to expose you. I'll probably do one extra lecture during the last week for people who might be interested. But anyway, this is an alternative way of initializing the members of a struct or a class. So before you even enter the executable block of the constructor, you do a colon, and then you set up the fields with data in a list here, so initialization list. So we take this new data parameter and we initialize data with it, that's the field. We take the left child and we initialize it to null, because when we first create a node, just like in a linked list, we want that null. And then same thing for the right child. And now all the fields have been initialized for this node using this technique called an initialization list. I want you to see this because you will see it again in your life, particularly if you do any inheritance in C++. But for our purposes, it's there simply so that you have seen it in live code. So that is an initialization list. And then notice here, root is a pointer to one of these structs, just like we did with the linked list. Okay, so here's the scary bit, is that for some reason there's these sort of mirrored versions of all of our functions. So we have a clear function up here, and then we have another clear function down here, but this one that takes a pointer to a node that I'm calling troot. Now we have an insert function. This one takes data. Notice that this one takes data and a pointer to a node. And then print, this one takes no pointers, this one takes a pointer to a node. So this is going to take some getting used to. But what we're trying to do is hide this pointer from the world. So we don't want people messing around with this root pointer if they don't have to. So we don't want to allow them to call any functions where somehow they would need to access the root pointer. So they just have to request a clear, and then we take care of the rest. So these all involve the root pointer, but the reason why you have these private functions is that we're trying to hide the root pointer from the outside world. And I'll just show you an example of how these work. So if someone calls clear on our tree, we're actually just going to fire off a process of clearing starting at the root. So inside of the actual implementation now we can actually pass in the root. And that fires off this version of the clear, which begins the actual work of clearing starting at the root node. But in terms of other programmers in the world, they don't need to know that that's what's actually happening. They're just going to call clear, and then we're going to handle the root pointer stuff without showing them. Same thing here. Inserting data is really asking this function to do the work. Notice that, by the way, this function returns bool. So inserting data from the public perspective is really a matter of returning the results of inserting the private one, which uses the root pointer to know where to start. So clear, where to start. Insert, well, we're not going to actually do the work to return the bool, so we're going to return the result of the private function that actually does the work starting at root. But for the outside world, they're just going to say, insert me some data and tell me if you could. So you can imagine print in order as well, and maybe I'll let chat do this. So this public print in order that looks so innocent is actually going to be, here's a hint. So what's actually going to happen inside the public version of print in order? Print in order starting at root. Good one, Shigam. Perfect. So they'll never see this, those other programmers out there in the world, but what we actually do is we start up the process of printing the contents in their ascending order with our private function. So you'll see this many times in your life in programming. We have public forms of a function that seem pretty innocent, but internally they're actually accessing all the important data. But this way, programmers out in the rest of the world don't have to worry about how it works. They don't have to worry about where it starts. They just ask me to clear, and I will handle that process starting at my root node privately. Same for all the others. There'll be a public form of it and a private form of it. The reason why there's no private form of get size is because the tree will always just have a count of how many nodes are in it. So that one's, what did I call that variable? Size. So that one's easy, right? That's just size. So we don't need a private form of that. We'll just return the counter. Good one, little peeper. Yeah, so you hit on that print in order starting from root as well. So we haven't actually done the work. I'm just explaining to you, why do we have two clear functions? Well, we have the one that the rest of the world can see, and then privately we have the one that actually changes our pointers around and makes new stuff and all of those things. Okay, so that's the start. Let's also knock out these things. So let's use an initialization list here so you can see how that's built. So we're going to initialize the tree with size 0 and root being null. So let's use an initialization list, colon, before the body. And some people will write it like this, which can be easier to see. So we have the size is 0 and the root is null pointer. So there I've used an initialization list for the trees data fields. But when I have this, not very much in C++, at least my style tends to be to just kind of put it all on one line like that. So there I've used yet another initialization list. So the tree's size starts at 0 and the tree's root starts at null. The destructor will just clear from the root as well. Okay, so we have a constructor done, we have the destructor done, we haven't done the fun parts yet. The size, I just did it because that's no fun. Talked a little bit about how the public functions that actually change the tree that remove nodes or add new nodes or look around inside the structure of the tree for things like printing. We have the public form that looks pretty innocent, and then we have the private form that can wreak all kinds of havoc. Because if you have this root pointer, you can wreak all kinds of havoc. Okay, so let's build one. Let's start with insert, and the reason to start with insert is because the other things it doesn't make any sense to clear nodes from a tree if you can't put any nodes in there. And it also doesn't make any sense to print nodes in a tree unless you have nodes in there. So I usually start with the insert. Okay, so this is weird because it's going to be recursive. Now you have to move your mind away from the big tree. Let me change the picture real quick. So when you're writing these algorithms in the private section, it can be helpful to not think about the whole tree anymore. So we have this thing called t-root. And what t-root is going to do is we're going to be moving it around this tree. So when you're implementing these algorithms in the private section of our binary search tree class, what you want to try to think of is that t-root could be any one of these trees. So t-root could be this tree, 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 or this tree, or this tree. So t-root could be pointing at the node that is at the top of any tree, or it could be one of these empty trees. So that's the thing to think about is once you get down into these private functions, don't think about the whole tree and what's going on in it. Just think about these smaller pieces. So for insert, we're trying to find a t-root that doesn't have any contents, meaning one of these subtrees that has no contents or is empty. So we're going to be moving t-root around until we find an empty subtree where our new data should go. So Shugam asks, do we need to deal with null pointer? And we most definitely do. So it's very important to bring that up and to keep it in your head. Null pointers are often our friend, but they can also be killers because they can lead to crashes, as probably all of you know now from the linked list, where if you get a null pointer in the wrong place, you're going to get a crash. So definitely we need to worry about null pointers. But in the case of insert, a t-root that's on empty, in other words, is null, is actually good. And then we'll be mindful of when null t-roots are bad and when null t-roots are good. So our algorithm is actually going to be walking down this tree to smaller trees and smaller trees and smaller trees until it finds an empty one that's in the correct location. So that's the thing to think about when we do this. Think about, did I find the little tree where I want to be? Okay, so to insert. So when do we know, based on t-root, that we found an empty tree? And Shugam already sort of hinted at this. So now that we're in here, don't think about the whole tree anymore. Just think this could be any subtree, anywhere. And we're looking for an empty one. So there's something about this argument that would tell us, hey, I found an empty subtree, and I can use that for my data. Null. Good one. So baby doll and Shugam. So if t-root is null pointer, good one, Tyler. This is a good thing for doing inserts because we're looking for an empty tree where we can add this data. So if we find that t-root is null, we found an empty tree and we can put the data in it. So in fact, we will just make it we'll just literally attach a node right into that empty spot. Size plus plus, return true. So that's the best possible circumstance. This is also, by the way, where a recursive function finds its base case. So once we find an empty tree, we literally just put a node right into it, increase the size by 1, and return true because we succeeded. Okay, so what if it's not empty? If it's not empty, there's 3 things that could be the case. So if I'm looking at a T-root that's not empty, and you don't have to say this in code, but what do I need to figure out how to do? Maybe if I bring my picture back up, I can help a little bit. So let's say we do insert 5. So if we do an insert 5, there you go, Baby Doll's got it already. So I may not have to do that. We'll just go back because Baby Doll already answered the question. Okay, so if we're not on an empty tree, then we're on a tree that already has something in it, and we need to figure out if what we have is less than, or what we have is greater than, or what we have is equivalent to the data, which would be, we don't want to do that. But we want to take that data. So if the little tree, that little subunit that we're on, already has a root node in it, then we need to compare this data with the data in that root node. And we'll start by seeing if it's less than. So then the trick is, well, what if it is less than? We actually need to use this function on a different tree. So the trick is to reset our operations from here to use a different tree. So how do we get, what tree do we go to from here? It has to do something with T-root. So if the data is less, we need to go which direction, in other words. Left. Good one. Oh, good one, Shugam. Baby Doll's right. So if the data is less than the data in that non-empty tree, that node, then we need to go to the left. So we're going to reset the entire operation. We're going to try then not to insert the new data into this tree, but into the tree down there. Now I haven't finished this line of code, but if we're on a non-empty tree, then we need to shift the operation to work on the tree down to the left. So the way we're going to do that is we're just going to go down to the left child of this tree, which is another tree, and try that one for this data instead. Now here's a heads up. This function returns a bool. So make sure that when you do a recursive call that you are returning its result. Now I think of this, by the way, as pass the buck programming. So if I found an empty T-root, an empty tree, that's my problem. I got to put the node in there, increment the size, and hooray, I succeeded. But if I'm on a non-empty tree and the data is less than the tree that I'm on, then I will pass the buck to the left child. Hey, that's your problem. This data goes somewhere in your tree, left child, not my tree, your parent, if that makes sense. But make sure that if you're passing the buck, that you return their result. So I'm going to return the result of inserting the new data on that child of mine. If the data is less, then it's their problem to insert it. Okay, so now we do the new data is it greater than, in this case we are going to do return insert, and then I'll let you do the fun part, which is what goes right there. So if the data is greater, that's right, so we're going to pass the buck to the right child and return their result. So the way I think of it is if you arrive on an empty tree, okay, that's my problem. I need to make a note for that data and increment the size. But if it's not, then I have to figure out whose problem it is. Is it my left child's problem? Is it my right child's problem? Yeah, basically. Your house is a leaf. That's true. I guess the town is. I think of a house as being a leaf, but it could be. But you're right. Oh, by the way, that's an interesting point, Shugam, about FedEx. So there's a very good chance that they use graph data structures and algorithms to figure out optimal routes. It's cool that you're thinking that way. Okay, so I either found a place to insert and did it, or I passed the buck to my left child and returned their result, or I passed the buck to my right child and returned their result. The only other possibility at this case, at this point, is that they are equivalent. If the data, if I haven't inserted it, meaning I'm not on an empty tree and my data is not less than and my data is not greater than, then it has to be equal to, in which case I ain't doing it. That's a duplicate and I'm not doing it. So that's your new data is equivalent to some data that's already in the tree, and we're done. Not doing that. So one of the beautiful things about a binary search tree is that's a very complex structure, and that takes care of the entire problem. These are very difficult to write by yourself, by the way. It takes a lot of practice to get comfortable with this. If you're already comfortable, then you're way ahead of the point that I ever was at this stage. But don't worry about it if you sit down and you, like, here's a challenge for yourself. Cut this out, don't delete it, but cut it and move it somewhere and see if you can rewrite this by yourself. It's a lot harder than it looks, but it is also excellent practice. Okay, so notice, by the way, every branch returns something. So empty tree, I do the work and I return true. I should be going to the left, so I return the result of passing the buck to the left child. If I should go to the right, I should return the result of passing the buck to the right child. The only other possibility is that I'm looking at a node that has the exact same data and I'm not taking it. So we're done. False. I won't insert it. Okay, that's insert. So let's try it on print. I will talk, by the way, about this ampersand up here. Although if someone wants to try to figure that out and share it Piazza, it'd be cool, but I will talk about it. For now, let's just worry about the algorithms and not worry about the ampersand. But I just will quickly tell you that that ampersand is the key to me inserting a node directly into that location in the tree. Notice print doesn't use that because I don't actually need to do anything into the tree. I just want to look. Okay, so here we go again. And again, I would just sort of point out to you that the whole problem here for printing is not to think of printing this whole dang thing, but literally just of printing one thing. So like this one thing, or this one thing. So the trick is, though, that every tree should only actually output itself and then pass the buck to everybody else. So if we look at this, if I were to just print this, if t-root is this tree, then I want to print the left child and then I want to print myself, and then I want to print the right child. The trick is that we need to force the left child to do the work for itself. So every tree can print its own data, but it's going to force its children to do the work for themselves. So that's sort of the way I think about the print algorithm. I'll print my own data, but your data is your problem. So let's see what that looks like in code. And by your problem, I mean the left child. So the parent will print their data, but the left child printing data, that's their problem. Same for the right child. So let's see what that looks like in code. Okay, so Shugam, let's use your note from earlier. What's the major deal breaker about T-root here? That we need to be careful of. Null pointer. So if you give me a tree that's empty, I'm not doing anything. I'm done. So I'm going to make my life a little simpler and say I'm only going to do something if you give me a tree that's not empty. So if you ask me to print data from a tree that's empty, I'm done. Okay, so remember that do we want spaces? Let's put spaces for now. Okay, so Little Peeper asks, where in the real world might you find a binary search tree? So this specific basic binary search tree, you wouldn't find it very often in the real world, but it is, it's the basic framework, the tree data structure. It's how we begin training you to implement data structures that are much more elaborate. And in the real world, where you find tree-like data structures are things like database products. So if you've ever encountered an Oracle database or a Microsoft SQL database, the data structures underneath those databases are tree structures. So they're but they are improved upon the basic binary search tree to allow for faster access. Yeah, so anything that's a database, that's a typical database, would be a tree structure. So this tree structure is not the best, but it's the first step in a building block toward fancier tree structures. So I think that at Oracle they use something called a B+ tree, and those trees improve upon these algorithms to make the access times faster. But they're still the same basic idea that they structure like a tree and they keep all the data in order, which is pretty neat. So yeah, if you were to go on in computer science training, by the way, this is related to Little Peeper's question. If you continue your computer science training, one of the next things you will do is you will take a binary search tree and you will implement algorithms to make them stay roughly balanced so that you have roughly the same amount of data everywhere in the tree, because what our tree right now could do is end up with all the data like going all the way down to the left, which loses all the advantages of the binary search tree. So the next step after this is to actually make it so that trees keep themselves roughly in balance, which gives you the advantages of the binary search speeds. And then you do things like, instead of storing one piece of data in a node, you store multiple pieces of data in a node, and then you have nodes have multiple children, which makes the trees sort of shallow up and also speeds up accesses. It's really neat. But anyway, good question. Okay, so I'm going to put some room here. I'm just going to print the trees. Every time I print a piece of data, I'm just going to print the data with the space. So at every location in T-root, it's only going to worry about actually outputting its own data. So, and the children data, we're going to make that do the work for themselves. So how do we do that? How do I make the children do the work for themselves. So remember, the children are also trees with roots. This is a harder one, huh? We don't worry about that. Close, Tyler. Close. So we're going to have a print in order. So we're going to pass the buck for the printing of our child's data to the left. So we're going to do... Somebody has to print in order before we print our data, and then... So we pass the buck to one of our children, and then we do ourselves, and then we pass the buck to the other of our children, and we don't worry about them being null or anything else. That's their problem. But notice that when our children get this function call, based on their own roots, they will also check their own roots to see it. So our children will use the same algorithm to check that they aren't empty. Isn't that cool? So who goes first? Which child do I pass the buck to first? Left. Good one, Damien. So if I cause my left child to print all their stuff, that's all the data that comes before me. And then after me, then I can print all the stuff from the right child. Exactly. And whether or not they're null or not, that's their problem. That's not my problem, that's their problem. But if you notice, my left child, if I can get this to click off, my left child's going to use the same function. So when my left child receives this command, it's also going to check to see if it's empty or not, which is crazy, isn't it? So left child's problem, I'm done. Print my own data, right child's problem. But the magic of this is that everywhere that you go in the tree, you're always getting the smaller stuff first, followed by the root, followed by the bigger stuff. Is that not crazy? So there's print in order. Before I do any experiments, let's do the clear. So yeah, these are hard. One thing though to challenge yourself is to, again, cut this, don't delete it, but cut it and move it somewhere and see if you can re-implement this. It's a lot harder than it looks. Okay, so let's do the clearing. This one's slightly different because you have to make sure that the children are cleared out before the parent is cleared out. So in the case of printing, we make sure that everything to the left has got printed out before we print ourselves out, and then we go ahead and let everything to the right print itself out. For clearing, it's a little bit different because we want to clear out the children before we clear out ourselves. So, yep. So let's go back a step, Shugam. So let's watch out for that T root. So what is the potential deal breaker with T root here that we need to be careful of? No. Good one, baby doll. So this is another one of those situations where we need to make sure that we are currently on an actual tree and not an empty tree. But if we are, then we're going to pass the buck. So left child, do your thing. Now it's your problem, and I'll wait for you to be finished. Right child, do your thing. And now it's okay for me. You should do this nulling, by the way. It's important. We're also, by the way, we just... oh, what am I doing? This is just clearing. I'm not removing a node yet. That's just clearing, just delete the thing. So make sure that your left and right children have had a chance to clear themselves out before you delete yourself. And again, you're passing the buck. So you're using the same algorithm for your left child. So when your left child receives this command, troot means themselves, and then they can take care of their own children if needed as well. Isn't that wild? It's a pretty cool thing. I want to take a minute or two before you, probably these are just going to work when you run the unit test, but I want to make a little program off on the side to see if it works, and also show you a trick in here. So I'm going to make another file, and I'm going to call it exp. No, I don't want to do that. Never mind. That's going to make pain. We won't do that today. Let's not do that today. No. So that was a mistake on my part. So this is just clearing. Shigam, you have a good point. Yes, let's do it. Let's go ahead and do that. It seems like this would be the safe thing anyway. So let's do that. Should be safe. Delete it, null it, reduce the size by 1. I think you are correct that we need to do that. So thank you, Shigam. Good point. Okay, these are tough, aren't they? They look so tiny and innocent, but again, if you have a chance, at least give it a try. Don't delete this code, but cut it and move it somewhere off to the side, and see if you can re-implement these things to get your mind in the flow of the binary search tree. So you may have other ways of explaining it to yourself, but for me, I always think about, like your first thought in recursive algorithms is, at least my first thought is, what breaks me, which in this case is nulls, and the other one is who else can I make do the work. So in insert, when root is null, I got to do the work, unfortunately. But in every other case, I can make other people do the work. And by that I mean other smaller parts of the tree. I can just pass the buck to them and make them do the work. That's how I explain it to myself. Okay, so everybody, Shigam's right. Let's restore the null here. That's going to be important, and also do the size minus minus. If you are paranoid, it would be acceptable to go up here to this clear function after you do the clearing and just hard reset the size in the root. Probably that's a good idea, just in case. In fact, it's said to do that. Okay, that's all the algorithms. I've used up a bunch of time, so I'm going to stop. So I need to find some time next week. In fact, next week what I might start with is like 5 or 10 minutes of just playing around with our tree in this state before we add stuff to it. And that's a good question. So do we not want this function to touch the tree? Well, we don't want outsiders to. So it's okay once we get in here to change data. We just don't want their function calls to force them to gain access. So imagine if they had to call my clear function with my root pointer. I would actually have to write a function that looks like this. And this is what I'm trying to avoid. So I don't want to have to be forced to give them a function that lets them have the root of my tree. So the main thing is to just avoid showing the root in the function call, but you can use it inside of the function implementation. So good question. I just want to make sure that third-party programmers don't need to do anything that requires them in their code to access my root. But once they've got me into my code, now I can access the root. Good question. I'll run it. Do I pass? Oh, it wanted all the it wanted the outputs on different lines. See, so I gave it all one list, and it wanted them all on separate lines. So let's go fix that. I put them all on the same line, and it wanted them on separate lines. So my print in order, I failed the test because it was supposed to do one value per line. Okay, so we just walked through the entire solution. So I hope that you used your time well. If you have it this week, you can spin up the driver for Project 4 because you know how to process commands. And you might even be able to sort of, no, you won't be able to do all of it. But you can at least begin setting up the command processing part, even though you won't have all the pieces you need for the actual project. And the other thing I guess you could do is sort of get yourself a look ahead on next week, or at the very least see if you can practice on these by taking the completed code, putting it to the side, and see if you can re-implement these things. They're hard. They take a lot of practice, so the more practice you give yourself, the better. Once you understand recursion, it's very powerful, and it makes total sense at that point. But everywhere right up to the moment when you finally sort of understand recursion, it's awful. So more practice is better. Yeah, good one, baby doll. Thank you. I needed that end line instead of the line break. Passing, passing, passing. I don't know what else I was failing before. Oh yeah, same problem. Okay, so thank you. That was a great. Thank you for interacting, and thanks for your ideas and answers, and the questions are all great. So this thing does not look as scary as it is to code from a blank screen. So again, if you can give yourself an opportunity to practice, low stakes practice, so you try your best and then kind of study what you did versus what we did together and see what's different and see if you can make some sense out of that. Okay, have a great week. Whatever you do for the remainder of the week, I hope that you enjoy it, or at least you have some time that you can enjoy. Otherwise, I'll see you next Tuesday night. It will be week 15, and we're getting down way on the small end of the semester. So everybody take care. Thanks, Tim.